everyone, in this video I will explain another popular supervised data mining technique called decision trees. Decision trees can be constructed using both numerical and categorical predictor variables and are used for both classification and prediction problems. I will start with a detailed discussion of classification and regression trees or CART method. First, I will explain our introductory case. Hayden Seller, the retail banking manager of Sunnyvale Bank, is interested in the reasons for the decline in the bank's home equity line of credit or HELOC business. Hayden doesn't believe that the decline is due to the competitiveness of the bank's interest rates. Hayden's intuition suggests they have not been targeting the right customers to market its HELOC products. Therefore, Hayden compiles data on 500 past customers. Hayden also collects the age, gender, and income from 20 new bank customers. Hayden plans to use the predictive model generated from historical data to predict whether these new customers will respond to a HELOC offer. So you can see on the screen some part of this big data set. And on the right side of the screen, you can see the decision tree of the same introductory case. In general, a decision tree represents a set of if-then rules. This figure shows a hypothetical decision tree applied to our HELOC introductory case example. The top node of this decision tree is called root node. The root node is the first variable to which a split value is applied. Here, our root node is age, and the split value is 50. Customers who are younger than 50 years old are placed in the left branch, and customers who are at least 50 years old are placed in the right branch. And these branches often lead to interior nodes where more decision rules are applied. In this simplified example, the income variable is an interior node. The split value for an interior node can be different. Here, the split value for income is $100,000 for those customers younger than 50 years old, whereas it's $50,000 for those customers at least 50 years old. The bottom nodes of the decision tree are called leaf nodes or terminal nodes, and this is where the classification or prediction outcomes are given. In this HELOC example, the leaf node indicates whether or not the customer will respond to the HELOC offer. Hayden now has 4 decision rules. The first one is, if age is less than 50 and income is less than 100K, then the customer will not respond. If age is less than 50 and income is greater than or equal to 100K, then the customer will respond. If age is greater than or equal to 50 and income is less than 50K, then the customer will not respond. If age is greater than or equal to 50 and income is greater than or equal to 50K, then the customer will respond. The bank manager, Hayden, then will apply these rules to future customers when marketing the bank's HELOC products. As this example shows, a decision tree sorts or splits the cases based on the values of predictor variables. Here, the predictor variables are age and income. At each node, potential customers are sorted or split into groups depending on their age or income. This process is repeated at each level of the decision tree until each subset contains only the cases with similar values for the target variable. This process is recursive because every split is dependent on the previous splits. For example, here in this figure, the split on the income variable is dependent on the previous split on the age variable. Each of the final 4 subsets, which are the green rectangular box on this figure, contains cases with the same value of the target variable, which is whether or not the customer will respond. A leaf node, such as these 4 subsets, is called a pure subset, where each leaf node contains cases with the same value of the target variable, and therefore there is no need to further split it. Like other supervised data mining method I discussed in the previous video, a decision tree is usually built using partition dataset. It's common practice to partition data into 3 sets: training, validation, and test datasets. The CART algorithm will first grow the tree using the training dataset by selecting the optimal splits of all predictor variables and all possible split values until no further splits can be made. This is usually achieved when all leaf nodes only contain cases that belong to the same class for classification trees or have the same outcome value for regression trees. In other words, the leaf nodes are all pure subsets. The decision tree produced in this step is called full tree, also called a full-grown tree or maximal tree, as it represents the maximum number of splits the CART algorithm can make to identify pure subsets. A full tree, however, tends to overfit the data, resulting in low predictive performance when applied to new cases. This is especially true for the decision nodes and branches close to the end of the tree, as these splits are based on a very small number of cases and tend to fit the noise rather than the underlying patterns of the data. Therefore, we use the validation dataset to optimize the complexity of the tree by pruning the full tree to a simpler tree that generalizes better to new data. Pruning is the process of removing branches of the decision tree to improve its ability to predict new cases more accurately. The pruning process results in a set of candidate decision trees with different levels of complexity. Then we are going to use performance measures such as misclassification rate for the classification tree or the root mean square error RMSE for the regression tree, and then compare to identify the tree that produces the lowest error rate called minimum error tree. The minimum error tree is the smallest, least complex tree that produces the smallest classification or prediction error on the validation dataset among all the candidate trees. In the following video, I'm going to show a couple of examples on how to build decision trees.